Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is You Ask, We Answer, a panel discussion on transformer testing. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the technical moderator for today's presentation and supporting you on any technical issues or questions for our panel. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and we'll integrate them into our discussion here today. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our host today is Damian Robinson, Regional Sales Manager. Thank you for joining us today, Damian.
Thank you, Michael. Thank you for the introduction to this series. For those of you who do not know me, I've been with Megger just under 13 years as both a territory sales and a regional sales manager, currently covering the Southwest region in the United States. I've been the North American sales team leader for the transformer product applications for the past 3 years, and I'm delighted to be your host and moderator today. You Ask, We Answer is a newly developed webinar series in response to industry travel restrictions due to COVID-19. What Megger has learned through various other webinar series is the industry continues to hunger for knowledge, and therefore, as opposed to educating on a pre-selected topic, this series was developed to allow you, the audience, to guide the discussion directly through questions. This is the second installment of this panel discussion where attendees submitted questions during registration. We will also encourage questions live during the discussion, which we will address as time permits. Previously submitted questions are arranged into topical areas, which we will discuss shortly, and we will address as many live questions as possible during the appropriate topic. The questions will be addressed by a panel of experts from Megger and other companies. Let's meet the panelists. First, we have Nick Pajanik. Nick is the Director of Operations for Weidman, a global supplier of transformer products and services, where in his role, he oversees the analytical testing laboratories and customer technical training. Nick makes significant contributions to industry standards through memberships in the ASTM, or American Society for Testing and Materials, Electrical Insulating Liquids and Gases Committee, the IEEE Power and Energy Society Transformers Committee, and SIGRI Dissolved Gas Analysis Work Group. Welcome, Nick.
Thank you.
Next up, we have Robert Brazil. Robert is the Senior Technical Advisor for Southern California Edison, a major electricity supplier servicing over 14 million customers, where in his role, he oversees transformer repair and testing at the Westminster Distribution Apparatus Facility. Robert brings 36 years of power transformer condition assessment expertise and is a leading authority on interpretation and application of narrowband dielectric frequency response in transformer condition assessment, authoring numerous papers and regularly presenting at conferences. Welcome, Robert.
Good afternoon, everyone.
Next, we have Dr. Diego Robolino. Diego is currently the Business Development Director for Megger's Transformer Application Products, aiding in developing leading-edge transformer testing technology. He brings over 20 years of expertise from the power systems, oil and gas, and research arenas. Diego is also heavily involved in IEEE as a senior member, Power Energy Society Transformer Committee member, and General Chairman of the Dielectrics and Electrical Insulation Society. If that is not enough, he is also a certified project management professional. Welcome, Diego.
Good afternoon, everyone.
Next, we have Jill Duplessi. Jill is the Global Technical Marketing Manager for Megger, where she is editor of the Electrical Tester magazine and primary author of the Transformer Life Management series, among numerous other duties. One of her more famous literary works is a book titled Electrical Field Tests for the Life Management of Transformers. She brings over 17 years of expertise in substation asset condition assessment through working in various roles with Doble Engineering Company and Omicron Electronics USA, as well as Megger. Welcome, Jill. And lastly, we have Dr. Peter Virelius. Peter is currently Senior Applications Specialist in Megger's Sweden factory, where several of the advanced transformer diagnosis products are manufactured. Peter is a leading authority on frequency domain spectroscopy, also called dielectric frequency response, developing the first field DFR tester in 1996, and is responsible for the advancement of DFR technology and applications at various other companies and now Megger. He actively participates in work groups and task force as a member of IEEE, SIGRI, and Swedish Transformer Standards Committees, particularly involved with dielectric frequency response, or DFR, and sweep frequency response analysis, or SFRA. Welcome, Peter.
Thank you. Pleasure to be here.
Okay, today's topics for the You Ask, We Answer transformer session will fall into the following categories of general testing, insulation testing, oil sampling and testing, winding testing, and a catch-all category that we're just calling miscellaneous. Let's get started with the first questions. So this first question will be in the general testing category, and it'll be for Diego Robolino. Diego, what are the minimum recommended required tests for installation of a new transformer?
Okay, for a new transformer, one of the things that we want to make sure is that we have all the information required to do some trending analysis in the future. I think that it's important to see also how critical the unit is. If it is just a pad-mounted transformer, of course, you're maybe not interested in too much information or too much testing, probably, but depends on how critical it is. Again, it might be a pad-mounted 3 MVA transformer, might be serving a hospital or special services unit, and that requires critical application. One of the things that we need to realize is if we look into the standards and we look into the recommendations, for example, SIGRI and IEEE, there's a diagnostic chart that you need to look at information that will provide certain level of diagnostics for every component in your transformer. So you want to make sure that you cover the mechanical, the electrical, magnetic, the dielectric regions of your transformer in a way that you can make a final condition assessment, okay? But if we're talking about critical units, again, I would suggest to do as much as possible, especially advanced technology testing like DFR, SFRA, your power factor testing. Make sure that you have all those dielectric components and electromechanical components integrated. Look into all the information that has been provided for field testing, right? These last couple of years, we had finalizing the IEEE C5793 document for installation of power transformers. So that is a very good guide to follow. Look into the IEEE C57152, which is the guide for field testing of power transformers. Those will provide you the best guidelines. But again, minimum required tests, I would say, make sure that you have enough information about the windings, the dielectric system, the electromechanical construction, and of course, that will be fundamental for you. And I think that Peter wants to complement to my response.
Yes, I will just focus on two things. One thing is the bushings. The bushing, you have usually the nameplate C1 value, the capacitance, and the power factor value. And it's pretty well known that this actual C1 value and the dissipation factor or power factor value will differ slightly when it's mounted on the transformer. So by actually measure the bushing when it's mounted in the field as a commissioning test, you will have your real reference value for the C1 capacitance and the dissipation power factor in the field. That is one thing. And the other one I would like to focus on is the Sfra, that actually I worked with Sfra for a very long time, and it's actually pretty complicated. And the reason that is complicated is that you very rarely have a good reference. So if you do a test when everything is installed during the commissioning, then you have a reference. Then the Sfra test in the future will have a value.
Yeah.
Thank you.
Okay, thank you. I forgot to mention that question was submitted by Joseph Testa. I will be reading out the the participant, who hopefully is online, in the future questions. So moving to the next question, this will be for Jill Duplessi, and this was submitted by Robert Bowen. What suite of tests do you recommend for a complete electrical snapshot of an in-service transformer?
Hi, Robert. Thanks for your question. Hopefully I have my mic on now. Sorry about that before. So for an in-service transformer, I'd say you'd need to do probably about 6 different tests to screen for any potential problems and to get a fairly comprehensive picture of the transformer's health. So I would recommend a DGA test or a dissolved gas analysis. And then not necessarily to perform in this order, but one of the highest recommended tests on my list would be a DC winding resistance test. This typically uncovers more problems than any other test you will perform. And then a power factor and capacitance test to screen for insulation problems. And here I would absolutely recommend that you supplement this with a narrowband DFR test, because it confers really compelling screening benefits. And by the way, many modern power factor test sets provide the capability to perform narrowband DFR tests as well as power factor tests. So it almost feels like you're doing one test. And since a power factor and a capacitance test doesn't check the insulation between winding turns, I also recommend an excitation current test, which will do that and much more, and not least a transformer turns ratio or a TTR test. And just like Peter had said for the last question, I would here also again emphasize the importance of testing the transformer's accessories as well, including its bushings and tap changers. As some failure surveys have indicated that together, these can account for upwards of almost 50% of power transformer failures. So for bushings, I would also recommend power factor and capacitance tests and narrowband DFR tests as screening measures. And then for tap changers, in addition to those I've already mentioned, like excitation current tests, ratio measurements, and DC winding resistance tests, I would perform dynamic resistance measurements. If you consider that an on-load tap changer transfers a transformer's entire load current from one tap to another thousands of times a year on average, there's a lot at stake if something goes wrong during one of those operations. So dynamic resistance measurements, taking a close look at what's happening during any given load tap operation. And a bonus is that with certain test instruments, you can perform dynamic resistance measurements together with the static DC winding resistance test, which makes it very convenient to include.
Okay, thank you, Jill. The next question is going to be for Peter, and this is from Amal Ashok. What diagnostic tests should be performed on a transformer after a major through fault occurrence?
Oh, thank you, Amal. I think I will start by before basically you have a trip of the station, and it's most probably the transformer, and it will take some time before you have people out there doing electrical testing. So I will start focusing on things that you could do immediately, and that is try to find the problem and what caused the problem. And then it's talking about, you know, looking on the relay protection, check recording of possible overcurrent, so you get a picture of what was actually the problem and what caused it. It gives you some indication what can happen with the transformer. If we're looking more specific to the power transformer, I think it's good to take an oil sample or check the headspace sample to check for combustible gases and do some oil testing, because you can take that almost immediately. Then if you come into electrical testing, it little depends in what you find out on the first. Maybe you have an external failure in the station and you have no really high current in the power transformer. Then you may limit the test on the power transformer if it's very critical to energize it. But if you have high current in the power transformer, it could also be a situation if it's a new or an old transformer. An old transformer is usually much more sensitive to short circuit currents. And then if you now come to the step where you actually would like to do a lot of electrical testing, then it's, you know, it's a discussion what is most important, but if you really start doing the test, it's good to take a fingerprint. But just mention things that is, you know, do insulation, capacitance and power factor. A lot of people talk about power factor and it's very interesting, but the capacitance is actually also, beside the Sfra, a good indication if something has moved inside the transformer. So if you, for example, see LG capacitance has increased or decreased, that will be a winding movement. And then, of course, Sfra. Don't forget, if you're looking on excitation current and TTR, is that when you have a short circuit, usually your core is very magnetized. And then it could be good to do the VRM with the demagnetization before you do the TTR and possible excitation current. Anyone that want to add something?
Yes.
Yeah, so just one comment. One of the standard procedures we see is a DGA test done immediately following a fault. And just to address the safety issue, you have to be cautious that if you get a DGA taken from the bottom of a faulted piece of equipment, you may not see those gases that are present from the fault. So we have cases that take 24 hours to 3 days for those gases to actually make their way to the bottom of the transformer and to be detected in a DGA. So Peter's comment was very valid, that if you have a faulted unit or a tripped unit and you can take a sample of the headspace gas, laboratories are equipped to test that gas, and that may actually be the earliest indication that you have a major fault and combustible gases present in the unit. So just be aware that limitation of DGA immediately following the fault, because it does take time through convection for those gases to distribute throughout the transformer.
Yes, Diego.
Maybe I would like to hear a little bit more from Nick on this question, because typically, talking from the operation point of view, I will look into, like Peter mentioned, I will look into my protection scheme, right, and what tripped. If it was an external fault to the transformer, if my differential protection tripped, then I know that it might be something internal. And if I have some combustible gases, then there might be some other safety concerns that I need to address. Can you tell us, Nick, more or less what the level of these combustible gases should be to be safe to do the testing?
Well, it's a little challenging because every gas, hydrogen, acetylene, ethane, they all have different combustibility limits. So what, for an example, was one of the transformers that we tested, we detected about 12 parts per million of acetylene 3 days later. But when we tested the headspace immediately following the fault, it was over 10% acetylene gas. So again, it has to do with how rapid those gases are formed. If they're large bubbles at the top of the transformer, they can immediately go to the top of the headspace, and you'll see alarms or pressure relays trip. So again, whether there's a bottom limit, you say 1%, 5%, it really depends on which gas makes up a predominant concentration of the total. So I would just say anytime you have a fault, a pressure relay goes off, you should really consider that the fault gas above that transformer in the headspace is combustible and act accordingly.
Thank you, Peter, Nick, and Diego. Great conversation. The next question will be for Robert, and it's a good segue. It says, where do you draw the line on returning a transformer to service or permanently removing from service? This comes from John Schnabel.
This is a very good question. We could probably go 5 hours on this question very easily. One of the things that I would definitely say is if your furan analysis shows you that your cellulose-based components are very seriously degraded and you're at the end of life, that's a condition that we cannot mitigate, and that's definitely a transformer that you're going to want to remove from service. If your leakage reactance shows that you have a difference in impedance from the last time you've tested it, that tells you that you've got winding distortion or possibly a core shift. So in that case, that transformer should be removed from service. That should also be validated by your SFRA. If your SFRA indicates that your winding has shifted, or we've got a problem with the core being shifted, then obviously that transformer is no good. If you do a visual inspection internally and you see that you have individual coil sections that have telescoped, or you have a significant shift in the laminations of the core iron, then that's something you're either going to have to do a major tear down, or you're going to have to salvage that unit. If you've got acetylene gas in your oil and it's due from a condition that you cannot mitigate, then obviously that unit will need to be taken offline and salvaged. If your key gases are elevated, like CO, CO2, et cetera, and the generation rate seems to be accelerating, unless that's something that you can mitigate with some type of repair, then that's a unit that you should salvage. Same thing with your partial discharge. If you're getting PD values that are rising and you cannot mitigate that, now some of that's going to be off of a bushing, but if this cannot be fixed, that's probably something you have to take care of right away. What generally happens is PD will start to rise, and the engineers will have a long discussion, and they'll have more discussion and more discussion after that, and then your transformer ends up on the 6 o'clock news or on YouTube because you didn't have a plan in place. But partial discharge, you have to take that very seriously. If your CHL at 60 Hertz is elevated and the trending shows that your rate of change is accelerating, that's probably an indication that this unit needs to be taken offline real quick. Now, if you have a unit that has shown a poor power factor and your narrowband DFR has looked poor, and let's say you go in and you change out the oil and you dry it out, and 9 months later that the geometric analysis of your narrowband still doesn't look good, that tells you that your cellulose is pretty much degraded and that unit needs to come out of service. That's the things that we would look at for like a GSU or a substation class transformer. If you're looking at distribution class apparatus, which is actually my expertise, for mineral oil filled transformers, we've found that the narrowband DFR is your absolute best diagnostic tool. And if we see that, well, we'll save the rest of that for we have another question that'll cover that. But for ester filled distribution apparatus, we find that these are very, very problematic in terms of condition assessment. What we have found is that everything that you know about transformers is almost useless when you try to do condition assessment on ester-filled units. The best thing I can tell you for a like FR3 or a Midel-filled unit is if the oil is clear and you don't see any particulates or it's not dark, you're probably okay. If the oil is dark or you've got suspended carbon in there, I guarantee you something horrendous had to have happened, because what we have found through our research is the natural ester fluids are almost bulletproof, and unless something horrible has happened, if that oil is clear, you're good. One other thing is that on distribution apparatus, if you have a flashed bushing due to an external application of voltage like a line transient, that level of transformer, that BIL level, is not designed to really handle a line transient of that type. So if we see any type of a flash over on the porcelain, that is automatic. We're going to salvage that transformer. So, like I said, we can go all day on this subject, and we'll still forget stuff. So,
Thank you, Robert. I do want to remind everyone to definitely make sure you're submitting live questions, as Michael explained earlier in the presentation. We do have a live question here that I will throw over to Jill. What is the sequence of tests recommended while performing testing on a transformer? And this is from Gurjeet Singh.
Okay, thank you for that question. You know, there's a lot of flexibility in the order of tests that you pick. And if you're really smart about it, if you know in advance the test you're doing, you could probably look at, okay, what's my test preparations for each test? And you could probably work it so that you order them so that you have maximum efficiency, which is going to change depending on the test you have to do. Now, one time we would say, yeah, perform them in virtually any order. Just whatever you do your DC winding resistance test last, because as a precondition to performing the test, you should saturate the core. But like Peter alluded to in an earlier question, I'm not so sure that that's such an important rule of thumb to keep in place. In fact, there's some benefits maybe in doing a DC winding resistance test if your test instrument you're using has the ability to demagnetize the core at the end of the test. Then you end up with probably a better bench line of core magnetization before you go on and do tests that are influenced by core magnetization, like excitation current or SFRA or even ratio testing. So there's some benefits to equalizing and getting that down to a demagnetized level. Transformer cores have, magnetic viscosity, which is means that they're never really going to stay at one level of magnetization indefinitely. So if you always take it down to the same place before you go on and do this test, then there could be some advantage in doing that. So yeah, today I'd say there's a lot of flexibility in the order, and there's really no right way on which test to do first.
Yes, Diego.
Just to add a little bit more to what Jill has explained right now, I think that before running any test on any unit, one of the things that I will do is always a visual inspection, just for safety, right? As a traditional procedure, just to make sure that there's no oil leaking around, that there's no any mechanical visual damage that could be on the transformer or anything like that, that may give me some additional information about the safety of the people and the equipment when running the test. And then, of course, it might be a different approach if you ask the question, we're doing this test because it's my every 5-year test, right? It's a routine test, or this is after a fault. So just keep that in mind. Mm-hmm.
Okay. Yes, Peter.
Just focus a little on that after a fault, that the test people I'm in contact with, they just say that it's specifically for testing a transformer after a fault, this demagnetization help to get value out of excitation current and TTR. So they have simply switched this, especially for after fault testing.
Okay. Great, thank you. Okay, we're going to move to insulation testing. And the first question is actually going to be for you again, Robert. It's, what is your recommendations for testing the insulation of internally connected Y-to-Y oil-filled pad mount transformers? And that comes from Kenneth Edmiston.
I would say the most important aspect of that is trying to find the anomalies that will occur on a single phase basis that may or may not be detectable using conventional methods. When you make when we perform a power factor measurement, you have to keep in mind that the CHL or the CH values that we're going to get are an aggregate average of the three windings together. So if we can sectionalize the core packages and get per phase CH or CHL values, we can find if we have any type of outlying problems that would be otherwise covered up in a normal power factor measurement. If you look at the October 2015 and the January 2016 issues of Electrical Tester magazine, there is a very good article in there on the delta Y cross-check method, which also talks about the YY method, where you can actually extrapolate per phase CHL and CH values to find anomalies which would otherwise be undetectable. As far as that probably about covers that, I think. Yeah, one of the advantages of the YY is that that cross-check method works especially well because you can actually do that from either side, from either the low side or the high side, you know, depending on the voltage class and the size of your transformer. So if anybody else has anything on that.
Okay. We'll move to our next question. Jill, can you please describe a successful power factor test, detail key values, and discuss what to look at when reviewing results? This is from Derek Holra.
Okay, thank you, Derek. This is actually a really good question. I'll try to be brief, but definitely feel free to contact me afterwards if you want a lot more detail. Sorry about the dog in the back. So I would describe a successful power factor test as one in which the test results accurately reflect the condition of the insulation system that you're interested in measuring. You know, this isn't always easy to accomplish because there are several externally introduced variables that may be influencing your test results. So then before I even head out to test an asset, I would be looking for previous test results because these are going to give me a good sense about the capacitance and power factor values that I expect to measure. Also, I want to make sure that I've executed my test preparations well because these are going to give me my best probability of getting representative test results. So once I finish my test, the first thing I typically do is give my results a very general look over for anything like really odd looking. So for example, really erratic results, maybe some high magnitude and negative power factor values, like maybe I have a 7% power factor here And over here, I've got a -2% power factor. I mean, these are really odd looking numbers. So these could be indicating that my transformer isn't grounded well. Or I would look for a charging current that is surprisingly low. For example, 1 to 2 milliamps or less. Since current and capacitance trend together and they're size dependent, if you're testing a really large power transformer with a good amount of insulation, you might expect, as far as charging current goes, 30, 40, 50 milliamps or more. It's really unique to the transformer, but it would be really atypical to instead get a milliamp or two, particularly if you're making a winding to ground measurement like CH or CL. So if that were to occur, that really weird result, then I'd have to reassess my grounding, connections, my procedures, and then repeat my test before I would go on to look at my power factor results. I should mention, though, on the other hand, if you were to measure 1 or 2 milliamps on an interwinding insulation system, CHL, for example, that might be a design explanation. But regardless, you should compare capacitance results to previous test values, if you hopefully have them, and they should not have changed by more than, I'd say, 1%. If everything checked out with capacitance, then I would look at your power factor results, and hopefully you have previous results, because that is the best way to evaluate power factor values. Plain and simple, power factor should not have changed from previous tests. But having said that, it's important to keep in mind that power factor is temperature sensitive. So for an effective comparison, you need to make sure that each set of values was accurately corrected for temperature, which is another discussion altogether. But I highly recommend that you use Megger's individual temperature correction, as I wouldn't really trust any other compensation approach. Also keep in mind that for winding to ground power factor tests, the bushings on the windings may influence the measurement. So if there's notable surface contamination on the bushings, or the condition of the bushings has changed between the tests, then this could be accounting for a change you're seeing in the transformer's winding to ground power factor from previous. Most test instrument manufacturers offer software that will perform a simple calculation to subtract the bushings from these measurements once you've tested the bushings separately, of course, so that you can see the winding to ground power factor without the bushings included. So I would look at those values. If you don't have previous test results to compare with, then it's a bit more challenging. And unfortunately, you'd have to default to power factor limits. And there, the standards groups offer suggestions on how different sized transformers should test. I guess my final comment would be a cautionary one. Keep in mind that some contaminants, such as moisture, don't immediately affect the line frequency power factor. So just because your power factor may not have changed from a previous test, that doesn't mean that you don't have a moisture problem developing. And for this reason, as I mentioned earlier to an earlier question, I would recommend you always supplement power factor tests with a narrowband DFR test, which provides earlier indication of developing problems.
Yes, Diego.
I just want to make a little comment here. One of the interesting things when you're doing power factor is also to look into the design specifications. There's some times where you can see a very low capacitance, like in the range of 100 picofarads, and that might be that you're facing an electrostatic shield. And we have had questions from people saying, I'm getting some weird results on my power factor, and I don't know what's going on. And especially, it might be that you have, for example, a 3-winding transformer, and the secondary is in between high voltage and tertiary, and then the secondary winding starts acting as if it was, right, electrostatic shield. So a little bit about the construction of the transformer is also interesting to know. It will help you also understand the values that you get on your power factor, the dissipation factor test.
Thank you. Thank you. Great. We're going to move to our next question, and this is for Peter. What is the maximum dissipation factor value acceptable for a transformer winding? This is from Irfan Ali.
Okay, hello. This is Peter Irfan. Jill and Diego took most of this in the earlier questions, so I will make a little different focus here. Referring to the IEEE field test guide, basically recommendation is not to exceed 0.4% at 230 kV and above, and below 230 kV 0.5%. And then you can say that if you're above that level but below 1%, then you need to monitoring it carefully, and above 1%, then it's very critical. As Jill mentioned, the problem is that moisture, for example, is not very sensitive at power factor. So you may use a 0.5% power factor limit, but it could be a well-dried power transformer that have a 0.5% power factor, and then it could be a quite wet power transformer with 3% moisture that have a 0.5% power factor. So typically, a core form high voltage power transformer, say about 230 kV when it's new, have about 0.22% power factor, and then 0.4, 0.5 is very high. But if you just change the design of the power transformer, especially if you do some shell form power transformer, or if you do distribution type transformer when you have a lot of paper between the winding and the cooling is between the winding turns instead of between the set of winding, then you may have a power factor above 0.5 also for a very well-dried power transformer. So generally, I would say that the IEEE 152 guidelines is valid, but I don't think this power factor is enough for new power transformer. This is field test values, and then it should be below that. If you are looking for accepting new power transformers, especially distribution transformers with a lot of paper between the windings, then you may accept higher power factor than 0.5%. And that is the situation when you have a lot of paper between the windings.
Okay, thank you, Peter. We actually have a live question that I'd like to ask you as well, Peter. What is accepted 10 delta values for bushings, and is there any standard for these? This is from Abhishek Sharma.
Yes, actually, bushing standards have acceptance value. To my knowledge, power transformer doesn't have any precise acceptance value in the standards. It's just the guide for field testing that have limits. Bushings have in the IEEE standards, they have OIP bushings, oil impregnated paper bushings, newly manufactured, should have a power factor below 0.5%. And I think RIP bushings, resin impregnated paper, should have below 0.85%. And if I remember, resin bounded paper, it's 1% to 2%. I'm not really sure. The IEC is a little bit different. IEC have 0.5%, no, 0.7% both for OIP and for RIP bushing. No sound will call in. You don't hear me?
You're okay, Peter. You're okay.
Okay. And referring to my last comment about the power factor limits for power transformers, I just want to mention that it's not only the dryness that determines the power factor. I know that it's very much depending on how you wind your bushing and how tight you put the paper. And I know example that actually same manufacturer design a bushing, OIP bushing, using the same paper, just using two different technique. And from one manufacturer, the typical power factor value for a very dry bushing is about 0.46. And from the other factory, it's about 0.23. And that is just the density of paper. And the only way to see if that bushing is wet or dry is to use lower frequencies like 1 hertz or 0.1 hertz.
Okay, thank you, Peter. Thank you. We have one more live question that I'd like to interject.
Damien, just to add to Peter, if the person who's looking into references for bushings, he can look into the SIGRE publication 755. That was the latest on reliability of bushings. There's good information about bushing limits for different type of bushings and different dissipation factor values.
Okay, thank you, Diego. Sorry, I missed your hand. I apologize. So the next live question I have will actually be for you, Diego. It says, how does the variation of the testing frequency with respect to temperature affect the response of insulations made of paper and oil?
Okay, well, we can go into some physics here of dielectrics and start looking into the different behavior of different materials with respect to frequency. And that's the beauty of working with spectroscopy, right? When we're looking at the spectrum of different materials as a function of frequency, when we are applying an AC system, right, an AC signal to a paper sample, we can see in the logarithmic scale that the response we get is basically a curve, right? And when we look at the dielectric response of liquid insulation, mineral oil, we get this in the logarithmic scale is kind of a linear response. So it gives us the understanding that the complex permittivity of the material, right, will be reflected in different ways depending on the bandwidth of the frequency and the polarization process that you are performing at that time, right? So especially when we look into the dielectric response and we're looking mainly into the interfacial polarization process, we see that the frequency, right, is affecting in different ways. That's the reason why sometimes just the capacitor in parallel with the resistor, it could work for the liquid insulation probably, but it will not work definitely for the paper insulation. It's a much more complex circuit for analysis. And frequency, of course, we'll look into the changes in the complex component, in the real component. And you will see that the real component of permittivity will change basically on the very low frequencies, right? When the loss component or the imaginary component of the complex permittivity will have changes from the very beginning. So that could be something that if somebody was asking about that, I would be more than glad to spend maybe a couple of hours on that. To have maybe a better guide, and Peter maybe can give a much simpler answer to that.
Yes, Peter.
Yes, I'm unmuted. Yeah, I try to make a little more an alternative version of the same thing. If you think about the insulation, like you have some kind of effect of polarization, it's like moving ions in the material. And basically, if you lower the frequency, you give these dipoles, ions, little more time, and therefore they become more visible. So for example, if you have moisture in paper, the moisture becomes more visible if you give this polarization effect a little bit more time. Alternatively, you could speed up processes by increase the temperature, and therefore lowering the frequency, which is giving it more time, is more or less the same thing as increase the temperature, which speed up things. So therefore, if you take a bushing, for example, the standard procedure in factories up to now is that, okay, I'm measuring at 50 hertz, but I know that this doesn't reflect my moisture very well at 20 degrees C. Therefore, I heated it up in the factory and I verify that if it's still a good, low power factor at say 60 or 80 or degrees, then it's a good dry bushing. Alternatively, you can do the same at 20 degrees, but instead of increase the temperature of the bushing, you lower the frequency. So basically, if you have the same or almost the same power factor at 60 hertz, 20 degrees C, and let's say 65 degrees C, 60 hertz, then it's no difference, then it's a good bushing. And the same thing, you can say that if you have the same power factor at 60 hertz at 20 degrees C as, let's say, 1 hertz or 0.1 hertz at 20 degrees C, it's also good bushing. If you get an increase of the power factor when you increase the temperature, it's moist or bad. If you get an increase of the power factor with lower frequency, it's also bad.
Okay, thank you. Thank you, Peter and Diego. Okay, next one will be for Jill. What should I do if I can't short circuit a winding in preparation for a power factor measurement, either because the bushings are enclosed or the neutral bushing is on the side of the transformer?
Okay, yeah, I like this question because for sure test environments don't always make it easy for us to do what we should be doing or want to be doing. So it is true that you want to short circuit all the bushing terminals on a winding together for each winding in preparation for your power factor test, for narrowband DFR, and for DFR measurements. So this in effect turns the winding, which is an inductor, into a test electrode. And that way voltage across the winding is the same throughout. And the current we measure in the test is the charging current required to electrically charge the insulation, and also the current that is given up by losses. If we don't short circuit the windings, then we would also measure an inductive current that of course is 180 degrees out of phase with the capacitive or charging current. And this would reduce the apparent charging current that we measure while the loss current stays the same. So therefore the loss angle would change and our power factor would change as well. By how much? It really depends on the transformer. So what if you can't physically short a winding? Because remember, when you short the winding, it's important that you have appropriate clearances from the grounded enclosures that might be surrounding a bushing, or from the tank itself. You have to have appropriate clearances from that shorting jumper and those surfaces, those grounded planes. Otherwise, you can get coupling to ground, and that can also introduce error into your power factor measurement. And I would not suggest, by the way, using a rubber blanket, sandwiching that in order to facilitate short circuiting the winding when clearances are really hard to maintain. So in those cases where it just becomes impossible to short all the winding terminals, I would make sure that the other windings are short circuited at a minimum. And if the new
We seem to have a little technical difficulty with Jill. While we potentially wait for her to reconnect, does anyone have anything else to add? Okay, we may come back to that when she gets.
I could probably it's Peter here. I could probably continue where Jill was going. Basically, what she started to say was that short as much as possible, and if one winding is not possible to short the other windings. Everybody, Jill, are you back? No, not yet. Okay, so short the other windings. So for example, if you have a high voltage winding and a low voltage winding, and it's virtually impossible to short circuit the high voltage winding, make sure to short circuit the low voltage winding at least, then you will get a reasonable power factor. And that is due to that the short circuit impedance of the winding is of course much lower than the excitation impedance. If the neutral is not possible, if possible, short circuit the phases together and leave out the neutral. But if all the windings are left open, then you will get an errorless measurement, at least down to, say, between 10 hertz and 1 kilohertz.
Thank you. Thank you, Jill. Hopefully it looks like you're back. Hopefully you're back with us.
Yeah, can I just check that you can hear me okay, Damien?
Yes, we can hear you just fine.
Perfect. Sorry about that.
That's okay. Thank you. that shows everyone that this is actually live. So occasionally we have hiccups. We'll move to the next question. Arun Raj asks, which is the best method for assessing the insulation condition of potential transformers? Diego, if you could take your first stab at that.
Okay, well, thank you for the question. Again, a potential transformer, you may have a different type of designs on the potential transformer. On the medium voltage side, we have tested several potential transformers, which are mainly solid insulation, okay? And the importance here is that the test that we have done is basically from the high voltage side to ground, where the majority of the insulation resides. And that is typical for a dissipation factor test. We carry out that one and DFR testing as well. We have identified several times issues with the materials, right, or the construction itself of the inductive type potential transformer on the medium voltage side. On the higher voltage side, of course, dissipation factor is the easiest way to go, right? You start looking again into the higher amount of insulation which is residing between high voltage and ground, and the reason is because most of the designs on potential transformers have a shield in between high voltage and low voltage winding. So if you try to do a high to low, the information that you get might not be accurate. Again, talk to the manufacturer, but most of the designs that I'm familiar with will have a shield in between. That's the reason why you will like to see between high voltage and ground. Mm-hmm.
Yes, Peter.
Yeah, you will just add that my experience is that the 50 hertz value for instrument transformer, both voltage transformer and current transformer, is usually quite low, even if it's relatively moist. And therefore, we have a good experience using DFR for that, and I expect also using narrowband DFR. But basically, even a relatively wet power instrument transformer may have a power factor of range 0.2 to 0.3%. It's just when the moisture gets above, say, 4%, when you get an elevated power factor at 60 hertz.
Okay, great. Next question, Peter, does negative power factor necessarily mean that it is an error in the measurement?
No. Basically, negative power factor is possible, especially, you need to, if you measure everything to ground, then it's like physically impossible. But if you have a UST measurement, negative power factor is possible. And it's mainly due to some combination of creep currents and capacitive coupling. Therefore, it's quite common on bushings, especially at lower frequency using DFR. In many cases, it's how to say, just a natural effect of creep currents on bushings, but it may also be an indication of a creep current that should either inside the bushing or inside the power transformer that should not be there. And referring to what Gilles mentioned earlier, it's like when you get very strange result, including negative power factor is a little bit strange result, then you should be observant and try to understand why. Referring to DFR, it's quite common to get slightly negative power factor at, say, 1 hertz and below. And if all your 3 bushings looks the same, this is mainly due to creep current, the oil combination of the bottom part of the bushing, and then it's not any problem. But if one bushing deviates quite a lot from the other bushing, then you should see the warning sign.
Great, thank you. Next question, how do I interpret narrowband DFR? Robert?
Okay, we're going to try and do an hour lecture in about 4 minutes. When we do a narrowband DFR measurement, we're going to take a series of power factor measurements between 1 and 400 hertz, and we're going to plot all of this information. We're going to put our frequency on the x-axis, and we're going to put our power factor on the y-axis, and we're going to plot our x-axis using a logarithmic scale so that the information doesn't get all compressed on us. Now, we're going to do both a geometric and we're going to do a parameter-based analysis of this narrowband plot. We're going to look at the magnitude at 1 cycle. We're going to look at the magnitude at line frequency. We're going to look at the slope at line frequency, and we're going to look at the point of minimum magnitude, or what we call the trough. This trough frequency is very, very important. Looking at the response, the area from 100 to 400 hertz is going to correspond to high frequency polarization losses such as electronic, atomic, or orientational polarization losses. And we're going to see the effects of winding geometry there also. If we look at the area between 10 and 100 hertz, under normal conditions, this is going to be dominated by the effects of the leakage that we see through the paper. Looking at 1 to 10 hertz, we're going to see the effects of oil and interfacial polarization losses, which is going to be also driven by winding geometry. Now, an early method of interpretation stated that if you have a positive slope at line frequency, then the transformer in question was considered to be in acceptable condition. However, this is an oversimplification because the slope at line frequency is going to be driven by the position of the point of minimum magnitude, or what we call the trough. Now, as the oil and the insulation degrades, that entire response is going to migrate towards the high frequency side of the plot. And that the point of minimum magnitude, or trough, is going to move proportionally. As a result of this, we are able to use that point of minimum magnitude as a marker where we can actually track changes in condition in the oil and the paper in your transformer. Now, if we have a sufficiently robust database, we can actually apply a condition classification to your transformer based on the frequency at which that trough resides. Now, in this operation, temperature correction is very, very important. And if you have a tan delta made by Megger versus other equivalent types of power factor testers, you have the ability to use the individual temperature correction feature within that tan delta, which will give you a huge leg up in determining the actual dielectric response of that specimen. Now, if you have a slight change in condition, that change may or may not be visible at 60 hertz, because at 60 hertz, that measurement is dominated by capacitance. Now, if we decrease the applied frequency, the capacitive current starts to drop out, while the resistive or conductive current remains constant. Therefore, your magnitude at 1 hertz is going to be very, very sensitive to any changes in condition in the oil or the insulation. As a result of this, we found that the magnitude at 1 cycle is actually a much better indicator of degradation than actually the value at 60 hertz. So much so that Megger has actually established upper limits for power factor of 1 hertz for, I know, condenser bushings and for like GSU and substation transformers. Let me check my notes here. Now, we talked about the the testing of the YY transformers earlier. Using the cross-check method. We utilize the narrowband DFR when we suspect that there may be some type of anomaly. But we can use the narrowband DFR using the open tap changer cross-check method to where we can now extrapolate a narrowband DFR response on an individual phase basis to get a CHL response for each phase separately. And as a result, we are able to find anomalies that would have been previously undetectable. Generally, what we'll do is, for example, a medium power transformer, 95 BIL, three-phase pad mount. The trough on that unit is normally going to come in at about 10 hertz, anywhere from 1 to 10, depending on our winding temperature. If we have one that comes in and that trough is at 40, then we're going to automatically perform that narrowband DFR in a per phase extrapolation using that cross-check method. And if we see we've documented cases where you'll have two phases where the trough is at 10, and the third phase that trough may be at 70, which means that you would have been unable to detect that anomaly unless you used NBDFR and you use the cross-check method. One thing that you really have to take seriously is, see, I have personally tested more than 8,000 transformers using narrowband DFR, and based on what I've learned, I can absolutely say without question that 60 hertz power factor testing absolutely scares me to death, because you cannot see anything using straight 60 hertz power factor testing. We've done a tremendous amount of thermal life, advanced thermal life testing on transformers with mineral oil and FR3, and we have found a number of cases in mineral oil filled transformers where the changes in oil are so rapid and the response moves so quickly from left to right, where in a lot of cases that 60 hertz power factor is no longer even a valid parameter. We have seen cases where we would put a transformer under load at 150% for a couple of months, and the power factor at 60 hertz would actually decrease versus increasing due to the movement of that dielectric response. So that's all I've got.
Yes, Steve.
I think I just want to add to the excellent description Robert just gave to this. Look in the logarithmic scale, especially because we're looking into this 1 hertz to 10 hertz. That decay will vanish if you don't look into the logarithmic scale. And as a visual effect, you can understand many things just by looking at the narrowband dielectric response, especially if you see contamination on the insulation system. You can see distortion on the dielectric response. So there's many different things that will pop up to your eyes just by looking at it. But again, you need to look at it on the logarithmic scale.
Yes, Peter.
Yeah, I just wanted to add also that this explanation of narrowband DFR actually goes hand in hand with, power factor testing. You do a very short frequency sweep to 15 hertz. You do a narrowband DFR to 1 hertz, which is 15 times lower than 15 hertz, or you do what we call full DFR. But we are also discussing what is full DFR. Typically on instrument transformers, we typically go to 10 millihertz, not to 1 millihertz, and certainly not to 0.1 millihertz. and for transformers with full DFR, we go to typically 1 millihertz. So basically, you can say that for 60 hertz, you have a very limited, how to say, assessment of your insulation condition. You miss quite a lot. If you go to narrowband DFR, you see a lot of more. And I would say that in most cases, you find most of the stuff. If you're coming more, really would like to go in the detail and assess actual moisture content level in power transformer, not just separated a good one from a bad one, which of course very important. Then you may use full DFR. So these methods is just like adding a little more, but you know, I really appreciate the narrowband DFR method.
Okay, there's a lot of questions we have on insulation, and unfortunately, we're not going to be able to get to all of them due to having several other topics we still need to get to. I do want to ask one more with regards to insulation resistance, so we could have a little bit of knowledge there. Peter, does a unit's insulation resistance of 1 to 2 gigaohms mean it's later in the life cycle? Is it dependent on what kind of asset it is? This is submitted by Josh Shantz.
Yeah, thank you. I not use insulation resistance so much, but if you wait for a long time and you get, you know, if you do insulation resistance, have a pretty good power transformer, you will after some time, you know, couple of like 10-15 seconds, you will get actually the oil conductivity, and then you will get the stable value for some time, a few minutes maybe, and then the insulation resistance go up. And basically, according to the Segre 445, for distribution transformer, the limit is like 500 megaohm, and for above 69 kV, the limit is 1 gigaohm. So if we go up to 2-3 gigaohm, it's somewhere in the middle, I would say. It's not catastrophic, but it's not very good. And since gigaohm is not really scaled with the capacitance, the size of the power transformer, it may mean a little bit different depending on the size of the power transformer. So I would say that it's a bit deteriorated, but not, it's above the catastrophic limit, put it like that.
Yes, Diego.
On the same thing, the insulation resistance, on the question, I don't see if the question is related to an oil impregnated system or it's a dry type transformer. That could be different as well. Maybe later we can clarify a little bit more about that. And again, insulation resistance is also temperature dependent. So make sure that, you know, the values are somehow referenced to a normalized temperature value. Okay.
Yes, Robert.
One thing you're going to find is that your winding insulation values are going to be very much dictated by the size of the transformer. If you've got an old, say like a very old B bank, 1 gigohm may be fantastic. If you have a 25 kVA overhead transformer and you have a high to low value of 1 gigohm, that tells me that unit has probably already failed. Now, one thing to keep in mind also, there are a lot of utilities now going to the natural ester-filled distribution class transformers. You're going to see a lot of very, very low values, especially when you're looking at low to ground, because of the different dielectric qualities of the oil. So you really have to really concentrate on developing a very robust database so that you're able to see what is normal and what is not normal. It's very, very important, especially when you start getting into the distribution apparatus.
Right.
Great, thank you. We are going to move on to oil sampling and testing. First question Nick, what are some best practices for field sampling and obtaining a representative oil sample?
All right, so pretty, you can hear me okay? Thumbs up? Got it. So it's a pretty standard question we have. ASTM has a document called D923, and it's a method that describes how to take a sample. If you do not have a copy of that, I recommend you get a copy. But what I'll really do is try to give you 3 kind of best practices here to as takeaways. Pretty important here for getting a good representative sample. First is adequate valve flushing. So ASTM recommends 1 to 3 liters of oil flushed through the sampling valve before you collect the sample. We know that doesn't happen because we'll go into field with clients and they'll take 10 samples and come back with 1 or 2 bottles of oil. So that's the number one thing I would say is at least at a minimum, make sure you flush out the sampling valve, the volume of oil in the sampling valve. The other thing with that too is we have situations where people will flush oil out at a very rapid pace. And what that actually does is can stir up particles and sediment and things that are in the bottom of the transformer. So we can see a sample that has a lot of sediment or particles in it, only to see the next sample with nothing. So again, it's consistency of sampling, making sure that you're flushing that valve appropriately. We do quite often know that this does not occur because we'll get a sample that has a very high moisture content, has a lot of sediment in it, and then they resample, and all of a sudden the moisture is gone, the sediment is gone, and they're wondering, you know, what's happening in the lab. So flushing the valve first is the number 1 takeaway. Number 2, this has become more important here, and we've recognized the issue in the last 2 to 3 years, but pre-rinsing of the bottles that you receive. So we know that there's a process for rinsing these syringes where you take the oil sample for dissolved gas and moisture, but the other tests, the dielectric breakdown, the power factor, color and visual, all the other oxidation tests we do are predominantly done from the glass or plastic bottle. Now, those bottles you receive from us or you buy on your own, they may be stored in your truck for a few days. They may get dust in them and dirt. We recommend that you actually add some of the oil to the bottle, cap it, swirl it, and dump it out. Pre-rinse those bottles before you take your final sample. We do get calls quite often actually from brand new transformers where there are particles detected in the bottle. So when we do a color and visual, we'll tell them that there's a detectable amount of particles and they're surprised. So those particles, the moisture on the inside of the bottles, they can affect your moisture, your dielectric breakdown, your power factor, and some of the other tests. So the second tip is to pre-rinse all your bottles. The other thing is, and this third tip here has come from the testing more often of oil circuit breakers and low tap changers, is don't reuse the Tygon tubing. So the small amount of tubing that you hook up to your transformer to drain into your syringe, do not reuse that. We found that even back in the 1990s, testing low tap changers, any residual oil left in that tubing may not be flushed out adequately, and you may cross-contaminate a transformer. So now that we detect less than 1 part per million, we report it 1 part per million, but any of those 0.4, 0.6, 0.7 parts per million, we want to be confident it was in fact from the transformer. So the last comment I'll say is make sure that you're getting all the information about the transformer. The new IEEE Diagnostic Guide for DGA does require you to provide the age or the year manufactured of the equipment. And the diagnostics now are very sensitive about in regard to the amount of oxygen in the sample. So we want to make sure that we flush well, we get an oil that's representative of what's inside the transformer, and that you record all the nameplate data so the lab can do a test properly. But with that, the comment I always like to say is the test results are only as good as the sample taken. And we know that quite often it costs more money to go out and take the sample than it does have it analyzed. So those are kind of the 3 tips: adequate flushing, pre-rinsing of your bottles, and do not reuse the Tygon tubing.
Yes, Diego. I think you're muted.
Yeah, I think I would like Nick to add maybe something else on that with regard to temperature of the sample. because it's all the testing that you do in the laboratory will have some correlation with temperature. And I think that that is a typical question as well. What is the temperature that I should provide to the laboratory about the sample that I took? Could you elaborate on that?
So, yeah, there's a few minutes there. I'm going to condense down to less than one. The temperature, ideally, if you could take the sample of the transformer with the oil at the same temperature every time, then you would be able to remove the fluctuations we see in the laboratory and data. We know that when temperatures are hotter, more gases might be in the oil than the headspace, and at cooler temperatures, there's a distribution that occurs. But with that being said, it's most important that you take the temperature at the time you took the sample the same and consistent manner every time. So if one time you read the gauge and it says 40 degrees C, and next time you stick a thermometer in the oil and it says 25, those may actually be the same temperature oil, right? But when you see the diagnostic report, one time it's going to say 40 degrees, next time it's going to say 25, and now you're thinking that these oils were taken at different times. So make sure you take the temperature consistently, the same way on all of your equipment, and in an ideal world, we take them at similar temperatures to be able to compare the trending and the history from one sample to the next.
Okay, thank you, Nick. The next question, I'm actually going to do a two-part question. Part of this was submitted by Jonathan Fox. The first part is, what are the most meaningful parameters for transformer oil analysis and how should they be analyzed? And then also the second part is, what do oil tests tell me about the condition of my equipment, my insulating liquid, and potential risks?
All right, a lot there. There's really one liquid test that provides information about the operation of the transformer, and that is dissolved gas analysis. There are many tests that provide information about the condition of the liquid. So dissolved gas analysis, or DGA, really allows us to identify past or current active faults in the transformer. So partial discharge, low or high temperature thermal faults, or arcing or sparking type faults in the transformer. But what DGA does, and the reason why we really emphasize DGA and why it's the most widely accepted test, is it really helps us identify if a fault exists. We do that by saying, are the gas levels that we're detecting in the oil above a threshold? Yes, if they are, then we have possible or probable fault condition. Two, we can use dissolved gas analysis techniques to also identify what kind of fault is occurring or has occurred in the equipment. And three, we can then look at the gassing rate, which is very important in the new DGA guide, that we look at the gassing rate of the individual gases to then determine the severity of the fault. So first you have to identify, do I have a fault? What type of fault could it be? And how bad is it? How severe is it? So really DGA is helping us identify if a fault condition is present, what type it is, and how bad it is, which then we can take corrective actions, do additional field tests, electrical tests, things of that sort. But again, all of those, that data we get from DGA does not tell us about the condition of the oil, right? They tell us about the condition or the operating condition of the transformer. There's about 25 different tests that we can do on the oil itself, and really about 6 or 7 that tell us and answer the question, is our oil suitable for continued use? So the IEEE has different guides for mineral oil, esters, silicone fluid, less flammable hydrocarbons that really look at tests like the moisture content. There's a couple of tests that look for oxidation of the oil, interfacial tension, acid number, color and visual. Those tests tell us whether our oil is aging. And then based on the amount of moisture and the aging byproducts in our oil, we then measure dielectric breakdown and power factor to tell us, hey, is our oil meeting certain insulation criteria, or has it aged and we're getting some loss of energy in the form of heat in the oil? Once those tests are done pretty much on an annual basis, you have kind of a flag points, if you want to call them, or threshold values that then would indicate, hey, we need to do additional testing. Once you have a suspected issue, there's probably another 20 tests that you can dig in further to really find out what else could be causing this. The moisture in my transformer, is it affecting my insulation? Is it affecting my dielectric breakdown? Where could the moisture be coming from? Moisture can be in a transformer real quick in 3 different phases. It can be individual water molecules in the oil. The water molecules can group together and form suspended droplets. Or you may have water come in through a bushing, run down the side of the tank, and be sitting in the bottom of the transformer. So if we have moisture detected in a transformer, that's a flag. Now we can do additional tests to see if it's affecting the oil. And obviously, Diego, there's electrical tests you can do to determine whether it's affecting the solid insulation of the transformer. So, but for most individuals, DGA and moisture are really the 2 that change most rapidly. And some of the other tests do not change as rapidly and can be more done on an annual or periodic basis.
Okay, thank you, Nick. And you started to hit on what the next question is from Christian Biaku. And what is the relationship between oil testing and electrical testing of transformers, and are both necessary? This could be addressed potentially by both Diego and you, Nick.
Yeah, so real briefly, and I'll let Diego take over. As I indicated, DGA, because it's a test you can do on an energized transformer or de-energized. If it's an energized transformer, it's a great snapshot to say, here's what's happening, here's the current condition, and again, a flag for additional electrical tests that you can do in the field. So if you have a high moisture test, Diego, you can then follow up by doing other electrical tests, correct?
And I think that one of the beauties of having the possibility to run an oil test is just it's energized, it's operating your transformer. You can just go and take a sample. Of course, they need to follow the procedures you just mentioned, right?
Right.
But besides that, I think that it is important to do both. And I think that it's interesting, the question, in the sense that you can go to your transformer every 6 months, right? Or once a year and take an oil sample and do analysis. And then you do your condition-based maintenance, right? Every 4 years, every 5 years, depending on the utility and depending on the maintenance procedure that you have in place. And then you do your full electrical and dielectric testing of your transformer. But there are many things to validate. Like you were saying here, Nick, of course, my DGA, if I'm looking into DGA is basically showing me an active failure condition, something that is happening while in operation of my transformer. And I can see, for example, that I have issues with the paper, issues with the oil. In which part of the transformer, that might be a different question. And that's where the complement of all this of this testing is. If I look into my oil dielectric analysis and I see that there is an active failure condition, and I see that there are gases, at different levels, I would like at a certain point to take the decision to say, okay, let me take this transformer offline and run a full procedure of electrical testing to validate these numbers. And I have seen many times that online monitoring is validated with laboratory testing on the same liquid insulation, and it's validated with the electrical field testing. And the beauty of, for example, looking into from power factor to narrowband dielectric frequency response to full spectrum dielectric frequency response, we have seen, for example, the correlation of certain gases being present in the system, right? By using the electric frequency response as well. We can see the deterioration of the insulation either on the solid insulation side or the liquid insulation side with a better spectrum with the electric frequency response. So this is the beauty of having both. If you are online, it helps you, the oil analysis, to do your condition-based maintenance, right? And to look into very specific testing, because now you can narrow the focus on the type of test that you will carry out in the field.
Thank you, Nick and Diego. Nick, we have one more question for you. This is a live question from Pranab Ghosh. Is it prudent to check the oil DGA of bushing and CTs?
Yes, it is. DGA can actually be applied to any oil-filled electrical piece of equipment. Back in the 80s, people kind of we got into deep conversations of whether DGA was applicable to low tap changers, because the whole idea was we were looking for fault gases that were generated under arcing type or overheating conditions, and that was obviously something that was going to be present in low tap changers. But since the early 90s and the acceptance of DGA and low tap changers, there are now C-grade guides with threshold values of kind of the point at which you potentially have an issue for bushings, and I believe there may be one for CTs. But the biggest kind of approach that we see in the industry is go ahead and test multiple units, those units that are running and operating correctly, test your problem units and look for deviations. But there is quite a few articles out there written about bushings and DGA, detecting partial discharge, issues with the foil lining inside of the bushings, arcing. We have clients that'll send us samples because they look at their bushings and 3 bushings are oil filled. There's a reservoir. They're gold, and dark. So we do DGA on the bushings, and we've actually been able to locate quite a few problems on bushings. So anything that's oil filled, we can do DGA on them as long as you can take a representative sample.
Perfect. Yes, Diego.
I think, of course, on like Nick just said, on anything that has oil, a DGA analysis can be run. It's a little bit complex in the field to take the sample, right, from a bushing or from a CT. Remember, of course, in these 2 units for bushings and CTs is not like in the transformer, so it has to be offline, first of all, right? Either one. We have worked with utilities in North America testing extra high voltage bushings and extra high voltage CTs. And actually, I do have some experience running DGA on just CTs, medium voltage, as part of my PhD work. So it is very interesting, the information that you can gather from those. It's really interesting, the behavior due to, like I said, internal active fault condition that might be happening, either bushings or CTs. The problem sometimes is if you don't follow a good practice, and if you don't have a good practice for sampling the oil from the bushing, then it may become a little bit cumbersome. But typically CTs do come with a valve to drain a sample of oil. Just need to make sure that you don't drain too much oil, right? Taking these samples, right, and leaving part of the insulation system, without the oil. So that's the only recommendation that I would give. And actually, if somebody is interested, we can share some of the work that Peter, myself, and Hydro-Quebec has done on both, with looking into some DGA analysis for bushings and CTs. Mm-hmm.
Yes, Peter.
Yeah, I just want to add to Diego's about bushings, that talking to the manufacturers there, if you do everything correct, DGA is proven to be very valid. The problem, especially on bushings, to take oil samples is, of course, the limited amount of oil in the bushing, and it's also that the gaskets for the bushing need to be replaced every time in the proper way. And the experience is that sometimes they do a mistake there, and then they actually damage the bushing, and they get water ingress. And the third problem is that a bushing typically has some kind of equilibrium pressure. So if you do a sampling when it's very warm, you actually lower the internal pressure, and then when it's cooling down, you get under pressure. So it's the procedure of taking oil samples on bushings is quite complicated, and therefore DFR for bushings are becoming more and more popular.
Okay, thank you, Peter and Diego. I will ask, we are at our anticipated time limit. We do still have lots of questions, and we're having to skip a lot of questions just because there's a lot of good dialogue, a lot of good conversation. If you can, I would ask that you could stay on an additional 15 to 20 minutes. We have about 5 more questions that I want to try to get to in the winding and the miscellaneous section. And so the first question is actually a live question pertaining to the winding section. What would be the root cause of the short circuit impedance test not matching with nameplate data? Robert, would you like to take first stab at that? That's from Abhishek Sharma.
A lot of times, what you're going to see is that the unit may have taken a fault, and you may have a geometrical change in your the shape of the winding. You may have coils that have shifted laterally, or you may have a section which is telescoped horizontally. If it's a three-phase transformer, I would definitely do a per-phase leakage reactance to see if you see any phase-to-phase deviations. So, it is not too uncommon, especially on transformers that are smaller, say, medium power, to where the nameplate may not match the actual tested impedance. It may say 5.5, but it may be actually 5.7. You do see that sometimes the nameplate is not stamped properly. But it's very important to do your temperature correction when you do that test, and it's also important to make sure you trend that and get baseline when you buy the transformer. So.
Yes, Jill.
Yeah, I agree with Robert, and would add that in the factory, when they do the short circuit impedance test, it's using a three-phase source, and that's injecting a current at rated current value. Where in the field, it depends on the test instrument you're using, but oftentimes we're just using a single-phase source. So sometimes, just because of the differences in the flux distribution between the differences in the source and the instruments, you can see differences from what's stamped on the nameplate because of that. And like Robert mentioned, again, you would never, based on a leakage reactance test result, you would never condemn a unit because it didn't match the nameplate. Because our three-phase equivalent test result in the field didn't match the transformer's nameplate, you wouldn't condemn it on that alone. You would go on to do individual per phase measurements and evaluate those before you would condemn for that reason, because there can be differences that can be explained.
Thank you. Thank you both for that. Next question, can a frequency response of stray losses test detect damaged continuously transposed conductor insulation resulting in a shorted winding? This is from Roldan Jacob Sabinorio. Jill, you want to take first crack at that?
Yeah, so first of all, an FRSL, or frequency response to stray losses test, is looking at losses like the name would suggest. Specifically, it's looking at the resistive component of a short circuit impedance measurement, and it's looking at this resistive component as the frequency is changed from, say 1 hertz up to 500 hertz. This test, its claim to fame is in its ability to detect a strand-to-strand short circuit within a singular turn. And so no other diagnostic test, like excitation, can't do that. It's really singular in that ability. Although I'd say in an SFRA measurement, you can pick out FRSL results. So therefore, you're still, at the end of the day, it's the FRSL test that's revealing that really unique kind of failure mechanism. So I get the question, if I understand it right, can FRSL test detect damaged CTC insulation on the actual winding being shorted? Because for short circuit impedance and FRSL, you're short circuiting the secondary winding. So the answer is yes. If the CTC insulation is damaged to the degree that it does result in a strand-to-strand short circuit, then FRSL will reveal the short-circuited strands on the winding being shorted. But it's a good question, and maybe, so if we were having a live conversation, maybe then the follow-up question would be, well, if that's the case, can I tell whether the short-circuited strands if my FRSL results are suggesting that I have them in a phase, can I tell whether the short-circuited strands are in the high voltage winding or in the low voltage winding of that phase? And to that one, I would say, unfortunately, no. It would be impossible to differentiate. But then, in that case, you'd ask yourself, well, maybe that doesn't really matter, because if I know I have short-circuited strands in that phase, either in the low voltage or the high voltage windings, my next course of action will probably be the same regardless. So yeah, long answer, but the answer is yes, you can see short-circuited strands even in the winding being shorted.
Thank you, Jill. Next question, what frequency ranges for Sfra measurement is recommended by the standards, and what is really needed for transformers? Diego? I think you're on mute.
Yeah, that is a question that it's quite typical. One of the things that you can remember is with the first reference standard for Sfra that we had on DLT 911, when they were looking only into the analysis of the windings, right? They were looking into frequencies between 1 kilohertz and 1 megahertz. Basically, that was kind of the expected range of analysis, because that was mainly focused on the windings. And if you remember also on some of the measurements that we could see down the road by, different practices on the grounding system, you could see that the higher frequencies, especially passing over 600 kilohertz, 1 megahertz, 2 megahertz, were difficult to repeat and get the same signature, but that was because of a bad grounding practice being applied during the measurement. So one of the things that IEC came up in the frequency response standard that they have published, the 67618, is the zero test. And that is kind of a very interesting test, because you can go and look also just looking at one specific terminal on your bushing, right, and see where your zero is. But I would say that generally speaking, it's been standardized to look up to 2 megahertz, having a good grounding procedure. And that way you can expect repeatable responses on your frequency response analysis.
Yes, Peter.
Yeah, just agree with Diego. Basically, common industry practice today is from 20 hertz to 2 megahertz. It's more difficult to get reproducible measurement on high voltage windings. Fortunately, the natural resonance of such high voltage windings is on lower frequencies, which means that for example, a 400 kV winding or even 230 and above, I would say that 1 megahertz is enough to at least assess. So basically measure 20 hertz to 2 megahertz, but when you look on the 230 kV windings and higher, don't care very much if it's different, say, between 1 and 2 megahertz. Assess them up to 1 megahertz.
Thank you, Peter and Diego. Okay, well, last question in the winding testing section. What is the frequency, and I believe this is related to how often, what is the frequency of doing Sfra test and partial discharge tests of a power transformer? This is from Ashish Gupta. And Peter, would you like to take that one first, please?
Okay, thank you. I take my point on that. I think it's quite different, Sfra and partial discharge tests. If we start with Sfra tests, an Sfra test is very, it's very important to get when you have, to detect the winding deformation. And it's very difficult to do that if you don't have a reference. So I would say that do a reference measurement when you commission the transformer. So you have a reference measurement. Then, you have a warranty period. Then if your transformer have a deformation that you have not caused any big issue, then it would be good to see that before the end of the warranty period. So I don't know the warranty period, but assume it's 5 years, I would do an Sfra test before the end of the warranty period. And if you have those two tests, I would say that every time you do a major work on the transformer, because Sfra basically detect almost all changes. It's very sensitive to detect anything you forget to connect again and things like that. And then, of course, the main is if something has happened, if you get some short circuit currents or something like that. So I will not really put it in the standard annual or every 3 years, or every 5 years. I will do it when you commission it. I will do it when before the end of the warranty, and then when needed. If you take the second question, partial discharge test, I would say that the partial discharge test for me in the field, it's quite complicated to do in the field for power transformers. So I would say that you do a partial discharge test when when it leaves the factory. That's very important. And then I would say partial discharge test, maybe you should require that to be done when you have put your transformer into some kind of service and workshop, to put things apart and put it together again. And then I would say put a PD test as an advanced test triggered by something else. You get a lot of DGA response that you need to explain and try to figure out. Then maybe PD measurements in the field have its place.
Okay. Thank you, Peter. We have 4 more questions that we'll ask, and we're going to try to finish up in the next 8 minutes. This will be some miscellaneous questions, and most of these are live questions. The first one is, would you provide guidance on testing dry type transformers? Robert, could you take first stab at that?
First of all, I would definitely be trending your insulation resistance. It's a really easy test to do. I would do that yearly, at least. I would also do a FRA on that unit as the baseline, and then if you suspect you have like a through fault, I'd double check it. At the same time that you're doing your insulation resistance, I would also do a power factor test, but I would do a tip up test also, because if you have any type of anomaly in there, you're going to see that trending upwards, or I should say trending downwards on trending upwards on your tip up. You probably want to do a winding resistance check every once in a while also, because you may have a Silphos joint that starts to maybe crack a little bit, or you might get some corrosion in there. If you have the ability to do some type of PD measurement, that will be very valuable. Thermographic evaluation also is very valuable when you're looking at dry type transformers. You may have some type of you may have a problem in the core, circulating currents. You may have a high impedance turn short that's not really showing up yet, but you might see it in a thermographic evaluation. And you might periodically do your leakage reactance also to make sure that you don't have something going on in there as far as winding distortion or something that you're not picking up visually. So.
Perfect, thank you. Second question, is a high pot test of transformer windings a destructive test? This is from Michael Main. Diego, would you like to take first stab at that?
I'm personally not a big fan of a high pot test on a transformer in service. There's different tests that are designed for factory. I don't know if it's related to field or factory. I will try to keep my testing the best possible way, you know, within the ranges of the power factor testing, insulation resistance testing levels, not stressing the windings, unless I suspect a damage on the insulation system. Then I would prefer to, you know, see the insulation being completely damaged during the test and not during the operation. Otherwise, any stress, any high voltage stress that goes beyond the rated value of voltage for that transformer will be destructive, right? And we got to be careful with that. We don't hear you, Damien.
Sorry, I muted myself instead of unmuting. Thank you for that first, Diego. Second, I was saying second to last question, Jill, I'd like to try to throw this to you. Is necessary power factor test on capacities less than 1,000 kVA? So yeah, is it necessary to do a power factor test on transformers less than 1,000 kVA? This is from Abraham Rodriguez.
Well, you know what? Robert's probably coming out of his seat to answer this one, because as he said, he's got an incredible experience with testing distribution size transformers. So I think I'm just, because it's wrong to not let Robert give you his opinions about this, but I'm pretty sure he's going to talk about narrowband DFR. But Robert, did you just want to answer the question?
You know, it's very interesting. When I was a technician, I started getting into doing a lot of power factor testing on what we would call medium power, 750 kVA up to about 5 MVA. Frankly, because I was bored, and started playing around with the delta Y cross-check method, and we found an absolute amazing amount of information that we would have never found otherwise by doing power factor testing on especially three-phase pad mounts. And we started playing around with the MBDFR, and we started going down on kVA values that we were doing. And I'm thinking to myself, this is a waste of time. And it turned out to be the smartest thing we ever did. We were able to do an incredibly accurate condition assessment on especially small, very small transformers using the narrowband DFR. You know, we'll have engineers come up and they'll say, well, can you tell me if this transformer was run hard? You know, this has been overloaded. And I would say, I can tell you what it had for breakfast. And that is how good, that is how valuable the power factor testing is on the lower kVAs, especially when you start doing the MBDFR.
Perfect. Thank you, Robert. Last question that we have time for today. Is there any value in testing the bushings prior to installation, and what is the best way? This is from Jeffrey Bliss. Peter, would you like to take first stab at this?
Was it prior installation or?
Yes. So is there any value in testing before they're installed on the transformer, and what would be the best way to do that?
I don't have so much experience with it, except poor experience, that usually when you try to test bushing not mounted, it's very sensitive for moisture, and I have seen a lot of people trying measuring good bushings outside, you know, try to take it out the crate and measure it. So my experience measuring it before installing is not so good, but honestly, I don't have so much experience with that. If someone else could add something. Yeah,
I may briefly add a little bit because we've been working with a couple of utilities just on receiving shipment from the manufacturer, and before they even put those in storage, they will test every single bushing for their facility. And it was quite interesting for them just to make sure the integrity of the bushing was there. There was no leaks, there was no issues. Typically what they will do, of course, is to remove from the crate. So never test with the crate, the wooden crate for transportation, because that may bring some losses into your test that you don't want to see. And then they will use a metallic tripod, right? Or just a metallic rack where they will locate all the bushings and do the testing. And like Peter said, you got to be careful about the moisture. And what they are doing typically is to do this test not outdoors, but indoors. That way they try to restrict at least as much as possible the influence of moisture. And they just keep these values just to validate information from nameplate, make sure that everything is within expected parameters. And also they are not looking now just at the C1, C2 capacitance value and power factor values. They're taking now focus on the narrowband DFR on the C1, not on the C2, but on the C1. They are keeping those records for future reference. So it's working in an interesting way.
If I could add one thing, basically resin impregnated bushing, oil impregnated bushing is sealed, just the bottom part and the top part. And the experience is that the bottom part of resin impregnated bushing is not sealed. And therefore there are some experience that especially resin impregnated bushing have stored too long time and get moist. That could be a catastrophic failure during installation. So I would say that it's maybe it's even more valid to do this test on resin impregnated bushing than oil impregnated bushing.
And to Peter's point, one last thing I would say, I've seen customers try to protect the bottom insulator of the bushing with plastic, and that's permeable. So I mean, it's really challenging to keep that moisture at bay. But so really important to check it before it goes in the transformer.
Great. Well, unfortunately, that's all the time we have today. We did go about almost 30 minutes over. There were a lot of great questions that we apologize we could not get to. I want to thank the panelists for being on and spending time with us, taking time out of your day. And I want to thank all the customers that came on board and spent the time with us till the very end. Michael, do you have anything else to add?
Yeah, thank you. And again, thank everyone for showing up to our presentation today, panelists and attendees included. As we wrap things up here, I'd like to go over a few things. We would greatly appreciate if you could take a couple of minutes to provide your feedback on our survey after the webinar concludes, so we can continue to improve upon our future webinars and panels such as this. On that survey, there's a field where you can also request a demo or a quote on any Megger products. Your certificate of attendance, a link to the video recording, will be emailed to everyone in about 2 business days. Additionally, you can view video recordings of previous webinars as well as register for upcoming webinars on our website at us.megger.com/webinars. With that, I'd like to thank everyone here for attending, and I hope you all have a great week.
Thank you, everybody. Enjoy.
Thank you.
Thank you.